Warm welcome, everyone. My name is Jens Hamler. I'm the faculty director of the Immigration Policy Lab here at Stanford. And I'm welcoming you to this inaugural seminar of our new monthly series, where we aim to highlight world-class, rigorous research on the scientific study of international migration. And very, very excited that you can join us today for the seminar. Before we jump right in, a little bit of housekeeping quickly. So the session is being recorded, and a recording of the presentation will be made available on the IPL website. We encourage you to ask questions throughout the talk. They will be coming straight to me. You can hit that Q&A button there at the bottom of your screen, and the questions will come to me, and I will basically moderate them. During the last 15 minutes, I will select a few questions. I will read them out to Michael, and then Michael should be able to answer them. If there's anything unclear during the talk, and a lot of people are confused, I might also interrupt him to give him a chance to clarify something. At the end of the webinar, we'll send a quick Google form in the Zoom chat where you can provide feedback, also suggest future speakers. This is an experiment we're running this year with this series, so we're curious to see what people think and whether they might want to see some other speakers in the future as well. So thanks for that feedback. And now it's my pleasure to introduce our speaker today. We are super thrilled to have Michael Clemens here, who's a professor of economics at George Mason University. And if you've been following anything regarding immigration research, you know Michael is a household name. He's one of the leading immigration scholars in the world who over 20 years has built this terrific research program on international migrations at the Center for Global Development in Washington, D.C., and arguably one of the most knowledgeable people about immigration policy worldwide. I remember last time I met Michael, he asked me about a random German immigration policies from like the 1980s that even I had never heard about. So he's very into the weeds here, and his research has won many awards, and we're very thrilled to have him. So Michael, thank you for coming, and please take it away.
Thank you so much. It's my honor to be here, but thank you more broadly for just creating this series. If it's an experiment, then it's one that I will be a big fan of, and I will be attending as many as I can. So this paper is about innovation in the United States, specifically about the effect of high-skill immigrant workers in STEM, science, technology, engineering, and mathematics on innovation in the United States, and a particular kind of foreign STEM workers, which is US trained graduates of US universities. I'm going to use a natural experiment to try to come closer, somewhat closer to identifying the causal effect of US trained foreign STEM workers on innovation in the United States. I'm going to talk a bit about background on what's been happening with innovation and international students. I'm going to talk about a policy rule that I'm going to rest on to try to approach causal identification and get to some estimates at the end. This is very much ongoing work, so I'm sharing the screen of a PDF slides, but it wouldn't be that much different if I shared my actual screen of what I've been working on this morning. And I really welcome your feedback on this ongoing work. So the policy experiment here relates to something called optional practical training, which many of you probably know very well. There could be people watching this who are on optional practical training right now, but I just want to give the background here. A 1947 law allowed students to have authorization to work in the United States, foreign students on student visas, authorization to work in the United States, usually used for things like summer internships or on-campus employment. In 1992, George Herbert Walker Bush, the administration of President George Herbert Walker Bush, explicitly created a legal authority under which foreign students in the United States on an F1 student visa could have authorization to work, not just during their degree, but explicitly after the degree. I'll just highlight the part of this rule which explicitly allowed a post-completion work authorization for in a limited way for 1 year, and this was a very flexible rule. want to get rid of that mark on your screens. There we go. This was a very flexible rule in that you don't need a sponsor employer. You need to begin work 2 months or less after graduation, but you can move from employer to employer. You simply have authorization to stay in the United States for a year and work, as long as the job that you take is directly related to the study, to the discipline that you graduated in. Two things happened over the last couple of decades. The number of OPT workers, the stock of OPT workers on the left who graduated with STEM degrees has skyrocketed. You can see it went up by a factor of 5 or 6 over that period. And innovation in the United States, as measured by patenting, also increased. On the right, you see the full universe of patents filed by inventors in the United States. This is patents where the lead inventor was physically located in the United States. And these are filings of patents that were later granted. So this is innovation in the sense that it was approved by the US Patent and Trademark Office as representing a real innovation. And that's why it drops off there at the end, because we're counting filings of patents that were later granted, and by definition, patents that were filed close to the right of this graph were not yet granted by the time I downloaded the data in March of 2025. But certainly an increase in innovation by that measure. What I'm asking is whether there's any causal relationship between these things. And the literature and common sense suggest that there could be a causal relationship, but that's what I want to investigate with not just full universe data on patenting, but on the data on the left are coming from what I think in the literature is a novel full universe database of all individuals on optional practical training between the year 2004 and the year 2022, including rich information about them, what discipline they studied, exactly not just where they studied, but where they worked, and what other visas they might have changed status to after being on optional practical training. Now, why the interest in optional practical training? First of all, because it's a major conduit for high skill immigration to the United States, particularly for US trained STEM graduates, foreign STEM graduates from US universities. This is a Sankey plot I made using the full universe data for the last 5 years of the data set, 2018 to 2022. You can see that for 100 foreign graduates on F1 visas from US universities, roughly 2/3 utilize optional practical training. This is in the full universe data. And a substantial number of those, about half of those, later at some point transition to an H-1B visa. This is not an annual transition rate. This transition rate from OPT to H-1B is people who once on OPT at any future point in the data set transitions to H-1B. So any change in OPT policy is going to have a first order effect on the inflow of high skill immigrants to the United States. Roughly 1/3 of new H-1B visas to the United States come from people who were once foreign students in the United States. So by any measure, an important flow. This flow is very likely to be severely restricted or even eliminated. So these are quotations from the new head of U.S. Citizenship and Immigration Services, Joseph Edlow. In May, he said that I want to remove the ability for employment authorization for F1 students beyond the time that they're in school. He said that in his confirmation hearing in the Senate. That is a synonym for OPT. He's saying I want to eliminate OPT. And a few weeks ago in the press, he said we've got to do everything we can to really make it abundantly difficult, only in certain situations, for foreign students to think they're just going to continue to live and work in the United States beyond the expiration of their F1 student visa. And it's been an explicit goal of the administration for quite some time, including in the final months of its first iteration, to terminate optional practical training, and it's likely to be terminated, or at the very least, very severely restricted. So there's a lot of policy interest right now in, well, what could be the impact of that, of such a policy change on the U.S. economy. Now, we have a lot of evidence about the effect of high-skill immigration on labor markets, on productivity, on innovation specifically. A lot of that focuses on H-1B workers, and that's very important evidence, to be sure. But what I want to do is try to learn more about specifically the effects of policy that affects international students, given that many international students don't become H-1B workers, and the majority of H-1B workers were not in the past international students. So these are not at all the same thing. And if we want to understand the specific effects of large policy changes that affect international students and their ability to remain in the United States and contribute to the United States, it's more direct evidence to look for natural experiments that affect international students specifically. What I want to do in this paper is go beyond individuals and organizations. A lot of the evidence that we have that relates to H-1Bs or that relates to other kinds of high-skill immigrants is measuring their propensity to innovate themselves as individuals, their spillover effects on laboratories or on firms. But there's evidence in the literature that the spillover effects go far beyond that. That they include a variety of indirect effects that can happen at the neighborhood, city, and even national level. And I want to start to address some of those as well. So the contribution I'm claiming here is that it's the focus on international students, so that we can get something closer to what Heckman calls the policy relevant treatment effect. Of all of the lates that we could be measuring, a policy relevant treatment effect, specifically of interest in a time when there are numerous policy restrictions on international students coming out of Washington, D.C. I'm looking to include spillovers between organizations and areas explicitly, and I want to do it in a way that addresses a major theme in the recent innovation literature, which is the difference between patenting and productive innovation. To what degree is patenting an indicator of economically productive innovation? So let me just start to motivate this work with the most tangible, easiest to conceive direct effects. Why would we think, by looking out at the real world, that international students who remain in the United States cause innovation? Well, most obviously, some of them just innovate themselves. Here's Rakesh Agrawal, who's a prominent scientist, received a medal from President Barack Obama and is well known in some circles. Here he is filing a patent 3 years after he graduated. He came first to the United States as a foreign STEM student to the University of Delaware 3 years after graduation. Here filing a patent, working at a private sector firm in Pennsylvania, where he is co-inventing a new method of extracting industrial gases, nitrogen and oxygen, from air. And another example, Kiana Aran came to CUNY in New York as an international student in STEM, and here she is 3 years after her graduation, co-authoring a patent that describes a new way to inject pharmaceuticals without a needle through mucous membranes. So the ideas and the creative capacity that are in the heads of people who come as international students and stay is clearly generating innovation in some measure. What I'm interested in is capturing spillovers. We have a lot of reasons in the literature to believe that there are spillovers to team members and within outside of the team within firms. A particularly striking one, Rebecca Diamond at Stanford and Shai Bernstein and their co-authors have a very remarkable paper that, if you haven't come across it, is one of the most interesting for me in years in this area. They get a remarkable database on innovation that they can link to Social Security records, and therefore are able to use unexpected deaths of immigrant inventors to ask when some exogenous event removes, unfortunately, from the world an immigrant inventor, what happens to innovation behavior by people that they have worked with in the past. And it strikingly goes down, and it goes down quite quickly. We have a lot of reason to believe that there's outside the firm, cross-firm knowledge diffusion within innovation hubs, not just diffusion through the air and through meetings and cafes, but workers going back and forth between firms in their heads, carrying knowledge diffusion within hubs. And even more indirectly than that, we can imagine mechanisms for spillovers with in which high-skill immigrants could provide tools and inputs that complement the production of knowledge through innovation without their names being anywhere near the patents. Think of a foreign entrepreneur who opens a group workspace, and in that group workspace, high growth startups begin, which are innovative and are patenting stuff. In a sense, the original founder of the workspace is catalyzing innovation, might be contributing to the rate of innovation, but would never be referred to in any way on the patent. We can also imagine demand-driven effects in which suppose a group of high-skill immigrants is involved within a cluster, such as a metropolitan area, involved in starting a variety of high-growth startups, all of which could use a particular input, a particular app, a particular hardware device, and an innovator, native or immigrant, identifies that opportunity and therefore patents something. Again, the people on the demand side, in this case, are catalyzing innovation without their names ever being near the patent. And of course, there could be simple labor market crowd out or crowd in effects. Immigrants could affect the innovation rate of an area or of a nation by crowding native inventors out of jobs in which they are producers of knowledge, or into jobs in which they're producers of knowledge. Lots of different mechanisms. I want to try to capture all of them because I'm interested in the policy relevant treatment effect, the total derivative of a policy induced change in the arrival of foreign students, or the ability of foreign students to remain and contribute to the US economy on innovation by all channels. So just to set up the most minimal framework we can imagine, I'll take a simple knowledge production function that goes back to Zvi Grilicus, takes its modern form under Chad Jones and Paul Romer, and taught in textbooks like Aghion and Howitt. Very simple model in which there's a flow of knowledge that it emerges from a stock of knowledge and a stock of L of knowledge workers. I'm just going to augment that in the simplest possible way by allowing there to be foreign and native knowledge workers that could be substitutes, could be complements in some completely agnostic production function. If I simply log linearize this, take the first order Taylor approximation and a total derivative, it's very intuitive that we can get to the seed of a regression specification in which the flow of knowledge, which I will proxy by patenting, is coming off of the stock of foreign knowledge workers. I'm going to scale by the working age population simply to eliminate scale effects in a way that allows a very simple interpretation of the regression coefficients in terms of just patents caused per worker. There are other ways to do it, but this is how I prefer it. And you'll notice that the regression coefficient that we're going to see, this beta is capturing both the direct compositional effects represented by the one in that equation of innovations that are happening caused directly by innovation that is occurring from these foreign knowledge workers, OPT workers who stay, become H-1B workers, become employment-based visas, visa holders, and are innovating themselves. And then this other term, which is capturing lots of ways in which they could shape the innovation of natives by crowding them out of the labor market, by crowding them into the labor market, by changing their productivity of innovation. in the way that that Shai Bernstein et al. Document. All of these I hope to be captured by this beta parameter. So how are we going to get policy? How are we going to get causal identification or approach causal identification, come somewhat closer to causal identification than normal? We're going to use a policy reform by the son of George Herbert Walker Bush, who many years later in 2008 created a large extension of the optional practical training program. It was originally, regardless of your degree, you could stay for 12 months. You could work for 12 months maximum. Starting in 2008, starting in mid-2008, you could stay for 17 additional months. That is a total of 29 months, if and only if your major was STEM. And this is a very closely regulated, precisely defined list of disciplines maintained by the Department of Homeland Security. It's pretty capacious. Economists are STEM, computer game programmers are STEM. If you work on explosive ordnance disposal for the military, that's STEM. Lots of things are comprised by STEM, but it rules out a large number of fields of study. And this is a really classic supply shock, because it meant that firms that, as of 2008, had already demanded certain workers could suddenly keep them for a longer time, in addition to getting more the next year, meaning suddenly the allowable stock goes up. This is what happened to the stock. This is the stock of OPT workers working at any given time in the full universe data. After April 2008, unsurprisingly, it goes up a lot. The solid orange line at the bottom here is non-STEM OPT workers on their 12-month OPT, which didn't change in 2008. The solid blue line at the bottom is, or in the middle here, is OPT workers on the first 12 months of OPT with their STEM degree. The dashed blue line is those people plus people who stayed an additional 17 months at first because they had a STEM degree, and in 2016 that additional 17 months was raised to an additional 24 months. That is for a total of 3 years rather than 1 year. OPT workers could stay. So this is this red short dashed line is showing the magnitude of the supply shock. This is an increase in the supply of STEM OPT workers specifically that is exogenous to any post-2008 shocks to demand for those workers. This is what the number employed would have been if demand had for a given graduate had stayed at its 2008 levels, and the employment had just been determined by the supply shock, and it's substantial. And just squinting at this graph, we can ask, well, is this large? Is it large at a national level? Is it the kind of thing that we might expect to see macro effects from? You can see that the shock with respect to 2008 is something like 125,000 additional foreign STEM workers at any given moment, because these are stocks. And we have to keep in mind that a lot of these people stay by other means. This also in the full universe data is in different years. The light green dashed line is the transition rate from OPT STEM to H-1B at any point in the future. That is, again, it's not an annual transition rate. It's the fraction of people who were on OPT in a given year who at any later point became H-1B workers. It's roughly half. And in some other work that I've done that we could talk about, I estimate that if you scaled up that number to include all of the ways that people stay above and beyond H-1B, such as marriages, asylum applications, all of the other ways that you can stay after OPT ends, even if you don't have an H-1B, you would get to something like a multiplier of between 1.5 and 1.63 if you want to know what the magnitude of the labor supply shock caused by an additional OPT worker is. So you could think of each OPT worker as representing something like 1.63 1.5 to 1.63 additional high-skill foreign STEM workers. How much is that? Well, in the American Community Survey, I think this month they're going to release the 2024 data, but this is the most recent that's currently available up through 2023. If we use the census definition of STEM workers and isolate currently employed high-skill STEM workers, that is people with a bachelor's or above, there are about 8 million in the US right now employed, 30% of that stock foreign-born. So just back of the envelope, if we want to know what's the size of this shock, 125,000 additional OPT STEM workers, scaling that up by roughly by 1.5 to include H-1Bs and the other ways that people stay. That would be something like a 19% increase in the number of overall foreign-born high-skill STEM, wherever they were educated, US educated or not, and something like a 6% increase in overall high-skill STEM employed in the United States. Not vast, but not tiny. Go ahead.
Michael, quick question here on the chat by Ahmed Gulek. He says, I believe H-1B quotas also increased in 2008. Firms demanding OPT and H-1B are often very similar. Can you separately identify the effects of those two changes?
H-1B quota in 2008, to my knowledge, in 2004, the quota was fixed at 65,000 original statutory quota plus an additional 20,000 for US trained master's degrees, and it has remained at 85,000 since 2004. So for this entire period, the H-1B quota has not, for the entire period of analysis we're doing here, the H-1B quota has not changed, which is quite remarkable, noting that there's a big positive supply shock to OPT workers. And as we saw, the transition rate to H-1B didn't change much, even though there's a fixed quota for H-1Bs. How's that possible? It happened mostly through cap exempt H-1Bs, which were exempt in 2004 and remain exempt now, which is nonprofits and universities. So that's how you can get a larger number of people waiting at the door for a fixed size of door with a constant transition rate.
Great, thank you.
Thank you. So 6% supply shock is sizable. It's not unreasonable to think that we should if these people are crucial in any way to innovation, that we should be able to detect that in aggregate data in some way. So how am I going to seek identification? I'm going to use geographic variation, and this is the basis for many of the crucial and highly influential H-1B studies, thinking of Giovanni Peri, Chad Sparber, and Kevin Shee, thinking of Curran, Lincoln, and Jolie. They often use spatial variation in CBSAs, census-based statistical areas, also known as metropolitan or micropolitan areas. If you're not familiar with these are basically cities. They aggregate counties. Zooming in on St. Louis here, you can see in the sort of center left of the picture here is St. Louis, Missouri. The settled area, the urbanized area, is in gray there, and a single border encompasses several counties to try to capture in the statistics for that CBSA what's going on overall in the metropolitan area. They're related to commuting zones, which are also often used in the literature, but the difference between them is that CBSAs are a perfect superset of counties, and therefore corresponding more closely to available statistics, whereas commuting zones are not. But you can think of the CBSAs as basically cities. So here is the geography of innovation in the United States. This is granted filings of later granted utility patents per 100,000 workers per year. This is a flow motivated by that extremely simple model you saw earlier. This is a flow of new knowledge coming off a stock of workers. And the reason I put this up is just to challenge the prevailing notion that this is really happening in Silicon Valley and Redmond, Washington. I mean, it is, and those are highly innovative places, but it's also happening around the University of Idaho in Boise. It's also happening in the Cheyenne, Laramie, Fort Collins, Boulder corridor at the border between Colorado and Wyoming. It's also happening in Columbus, Indiana. That's one of the highest patenting per capita CBSAs in America, where Cummins Incorporated and a polytechnic campus of Purdue and other institutions have formed a major innovation cluster. It's also happening in Research Triangle in North Carolina. It's happening in upstate New York. It's really happening. There is innovation across the country, and we have quite a lot of geographic variation in that. Now, just glancing at the distribution of the full universe of OPT STEM workers in recent years, this is again per 100,000 workers to try to control for in that very basic way for scale effects. And again, yes, OPT workers are going to Redmond, they're going to San Jose, excuse me, but they are going all over the country. OPT workers really are present in innovation clusters and private sector firms all over the place, in Tennessee, in Georgia, in Northwest Arkansas, in Pennsylvania, in Minnesota. There's quite a rich geographic variation in these things. So you can see the very simple identification strategy I'm going to use. I'm going to use a basic shift chair design with one unique aspect, which is that the shift here is not going to be the standard nationwide inflow of OPT workers. It's going to be, the shift is going to be disciplined by the policy rule. The policy rule took whatever stock was demanded by the firms across a CBSA in 2008 and augmented it by, in a way that is exogenous to post-2008 demand shocks, by a factor of 2 by the next year and a factor of 29/12 by the following years, until, as I mentioned, in 2016, under the Obama administration, it was further increased to a full 3 times the original 12 months. So I'm going to construct a shift share instrument from that policy rule times the stock of OPT STEM workers per capita in a given CBSA in 2008 at baseline. And just do a very simple regression specification, again, motivated by that very minimal model you saw before, in which in the second stage, patenting per worker is regressed on instrumented OPT workers per worker, where OPT workers are instrumented by that shift share instrument, and there are metropolitan area and year fixed effects. Incredibly simple, minimal specification. And many of you know well the shift share literature and how it has been turned upside down in the last several years. Wading into a shift share paper at this moment in intellectual history is a brave thing to do, but I do want to point out some of the methods suggested by some of the leaders in that literature, Paul Goldsmith, Pinkham, Kirill Borstyak, and others, and how we can explore those kind of that kind of much needed transparency in this literature in the context of these estimates. So core estimates of that incredibly simple regression specification. If we do the most naive thing and just take a CBSA year panel of patent applications for later granted utility patents per 100,000 workers on the left-hand side, and on the right-hand side, the stock of OPT STEM workers per 100,000 workers, that is per 100,000 working age population in that CBSA, we'll get in the first column, a large and positive and statistically significant coefficient that, of course, could reflect all kinds of causal relationships, not the least of which that very innovative places would be likely to attract OPT STEM workers to them. The coefficient declines quite a lot, as we might expect with that prior, if we just add in CBSA fixed effects and year fixed effects in the second column. And if we then just use the instrument in that exact same specification, exact same sample, we get a coefficient of 0.142, whose magnitude I'm going to discuss. This is the reason that I'm doing it in this linear way is so that we can interpret very transparently that coefficient. This is a number of patents per year per OPT STEM worker, and instrumentation is actually quite good, but just to address concerns about weak instrumentation, I'm showing the Anderson-Rubin p-value by any standards, even in a mode of analysis that is robust to weak instrumentation. This is a highly statistically significant result. So I want to explore what that coefficient means and run it through some of the transparency tests that the new shift share literature requires of us. The first, and this one has been important in the literature on H1Bs, is that we want to be really sure that this is not simply that a lot of stuff is happening on the West Coast and all of this is being driven by Silicon Valley and Redmond. And so the first thing we might do is something that Perici and Sparber do in Jolie 2015. Quite a demanding specification is to put in a full set of census region by year. I believe these are 9 regions, 9 census region by year fixed effects, absorbing all of the variation that is going on between regions. So what's left is only variation happening within the census regions, the 9 census regions that you see before you. The first column here is exactly the same IV specification you saw. The second one is including full set of region by year fixed effects. The coefficient declines a bit, as you might expect, but not by much. I mean, the large majority of the magnitude of this relationship is happening within regions, which is striking. And another way to address some of the to partially address some of the serious concerns in the recent literature about dependence of the result on a few specific shares. And intuitively, we would just want to know, is this just being driven by Silicon Valley? And if I simply drop the top 5 CBSAs in terms of patenting, which does include Silicon Valley, as you would expect, the magnitude of the coefficient goes down. This relationship does not evaporate, and I'll show you in a minute a more transparent way to assess that. But these are 2 things that have two specific tests that have been important in the H1B literature. So I just want to show them because it's quite standard. I do want to point out that some of the concerns, some of the specific concerns about the shift share design from Rodrigo Adão in the QJE and from Kirill Borziak et al. in Restud have been a particular concern about what happens to the internal validity of the shift share design when the most of the nationwide shift that you're looking at comes from just a few of the shares. In the reductio ad absurdum, if all of the OPT workers were going to Silicon Valley, then the entire nationwide shift would be Silicon Valley's shift, and whatever made the shift in Silicon Valley endogenous would also make the nationwide shift endogenous. That specific concern does not apply to this research design because, again, we're not using a nationwide shift in the number of OPT workers who came in for some reason. We're using a policy rule that determined the nationwide supply shock. What we need to be seriously concerned about is the potential for endogeneity of shares, but not of the endogeneity of the shift, which in this case is a kind of Maimonides rule style policy rule. One of Kirill Borziak's et al.'s suggestions is to just go back to basics, that for transparency, we need to go back to Angerson and Pischke's mostly harmless econometrics, where they recommend for all designs of this kind, we show what they call the visual IV plot, which is simply a partial residual plot of the first and second stage. That's what you're seeing here on the left-hand side. After partialing out CBSA fixed effects and year fixed effects, that's on the vertical axis, the regressor, OPT STEM workers per 100,000 working age population on the vertical axis. On the horizontal axis, the policy rule shift share IV. You can see, just looking at that, this is a very strong instrument, and it's not being driven, and the strength of the instrument is not being driven by just a few CBSAs. The second stage on the right is also suggesting that this is not a relationship that is being driven by just a few CBSAs. There's a kind of variation that is happening across the scale of exposure that is consistent with this relationship. And notice that what I'm showing, the line fit that I'm showing is a fan regression. It is a local linear regression of degree 1 with a bandwidth of 50 on to the right and 50 to the left of each point on the x-axis, meaning that the slope in that center region, which corresponds to the coefficient estimate of 0.142 that you saw in the tables, is not being affected at all by the very low and very high observations in this figure. In fact, if you squint at it, you can see that the low and high observations, if anything, are attenuating the coefficient rather than exaggerating it. So this is a kind of transparency that we really need more in the literature, as Borsiak et al. Point out. But this suggests to me that the relationship is not being driven by a few of the shares. What we need to be really concerned about in this setting is endogenous shares. We're basing this entire research design on the idea that even though more OPT workers might be going to areas that were more innovative in 2008 at baseline, that doesn't mean that those CBSAs were on some different long-term trajectory predating treatment. And this is a kind of plot suggested by Brant Calloway et al. In a great working paper on the continuous differences with continuous treatment research design. Here I'm just taking the top quintile of baseline exposure is the thickest line at the top, and then below that the second, third, fourth, and bottom quintile of baseline exposure, and just asking, look, were there differential trends in levels? Were there differential levels and differential trends of patenting prior to baseline? Obviously, differential levels, the places where more OPT workers were going in 2008 were highly innovative places relative to the rest of the country. However, there are not clear pre-trends here. And there, in the paper, I have a more rigorous version of this, but you can just, labor economist Richard Freeman used to say to all his students, whatever your finding is, I'm not going to believe it unless I can see it in a scatter plot. So this is just a very clear visual demonstration that there aren't sharp pre-trends between these very different baseline shares. This is not an RCT, so this to me doesn't prove that a causal relationship. It does suggest, it does provide some compelling evidence that should move our priors, I think, toward the idea that the coefficient estimates you're seeing are consistent with a causal relationship. But of course, it's always possible that something else that differentially impacted CBSAs happened at the same time, coincidentally, to this policy change, and that's not possible to strictly rule out in a research design of this kind.
Michael, there was a quick question in the chat was about whether the previous result would hold up if you put in state economic areas, fixed effects for state economic areas.
It's like state by year fixed effects rather than census region by year fixed effects?
Exactly, yeah, that's how I understood the question.
That's a great question. I don't know. I think that Perry et al. Jolie 2015 did both, but the reason I did region by year is because I think that is the main thing that they try, which is already a really demanding specification.
Yeah,
but yes, we could further saturate this with state level fixed effects, and that would be useful to know. Always useful to push an empirical result until it breaks down and try to understand why it broke down at that point. So thank you. Mm-hmm. Because this is not an RCT, and because the possibility of endogenous baseline shares remains something that is emphasized in Paul Goldsmith-Pinkham's excellent work in this area, is the necessity for transparency of really running lots of placebo tests. So this is something I'll do now. Again, in the first column here, that's just reproducing the core IV specification you've seen many times. There's a great placebo built into this this data set, which is that, as you saw, we have not just the full universe of STEM workers who were affected by this policy change, but we have the full universe of OPT workers who are non-STEM graduates who weren't eligible for this policy change. So that suggests a natural placebo, which is to add to the regression a placebo shift share, which is OPT non-STEM workers instrumented by a policy change that didn't happen. That is the baseline shares of OPT non-STEM times the that F scaling factor, which happened for STEM workers but did not happen for non-STEM workers, and see what happens to the coefficients. The standard errors inflate quite a lot, as you can see, but notably to me, the magnitude of the relationship between OPT STEM workers and patenting doesn't change much. So this is suggesting that there's quite a lot of spatial overlap, which doesn't surprise me, between where OPT STEM workers go and where OPT non-STEM workers go. But it also is an interesting and notable placebo test, in that if I was seeing a placebo effect of non-STEM workers on patenting, that would suggest that something else about these areas, including confounding shocks that happened, that were part of some sort of long-term propensity of these areas to be affected by a shock that happened in 2008, is not a first order confounding these results. The second placebo test I want to do is ask, well, look, if this is a real result, I should not be seeing equal effects on all kinds of patenting. So after looking for days in the literature to find and failing to find an existing classification of patents by their STEM relevance in some objective sense, I just made one up. In the patents view data from the US Patent and Trademark Office, each patent is labeled with a cooperative patent classification code, a CPC code. And so I just hand-coded a made-up classification that seems plausible to me, but I wish it had more of an objective basis, for CPC codes that are directly relevant to STEM work, in that making the innovation requires you to be doing science, things like biochemistry or nanotechnology or working with semiconductors. It's really not possible for somebody who doesn't have extensive STEM skills to be innovating in this area. I made up an indirect benefit category, in that if you're working on aircraft and aviation, certainly there are aspects of that of innovation work related to aircraft that would absolutely require a high degree of STEM training, and others that might not. And then a category of low benefit, if you're working on footwear, if you're working on cleaning and grinding machines, if you're doing woodworking, working in the sugar industry, you could be substantially innovating even without necessarily having extensive STEM training. And so I see the test of looking for an effect of OPT STEM workers on low relevance patents as a kind of placebo test. And you can see the dependent variable mean in the third to the bottom row of this table. The treatment effect as a fraction of the dependent variable mean is a lot lower for these low benefit patents. So to the extent that my made up classification captures in some sense the STEM relevance of the innovation work, that too is an informative placebo test. And again, I would have been bothered if the magnitude of this innovation relationship were similar between woodworking and nanotechnology, and it certainly is not. So let's do a sanity check on the magnitude of these coefficients. Is this something even remotely reasonable? Well, if we take the 0.142 figure to represent the causal effect of additional OPT STEM workers on patenting, noting that about 50% of them become H-1B workers, and then in estimates I've done in other work, an additional 13 percentage points remain long-term in the United States by other mechanisms, marriage, et cetera, all of the other ways outside of the H-1B process that you can end up staying. We could think of that being 1.42 patents caused by something like 1.63 high-skilled foreign STEM workers, which comes out to 0.087 patents per worker per year. So how reasonable is that? Well, from Hunt and Gauthier-Loisel in Jolie, we have a direct observation from the National Survey of College Graduates of patenting done by, patents filed by STEM workers who remained long-term in the United States, but came originally as foreign students. And the wave of the National Survey of College Graduates that they use asks about patenting in the previous 5 years and the number of patents filed by that person. That their estimate implies a per person per year patenting rate of 0.04. So this would suggest that first of all, these are of the same order of magnitude, which is somewhat reassuring. Second of all, this is suggesting that all of the indirect effects that we discussed add up to something that is roughly double what the individual level effect is. That to me is intuitively plausible. It's not wildly outside of the range that we might expect. And not just that, but it suggests that even though in those indirect effects you saw room for positive and negative effects. For example, we could expect a negative effect if OPT STEM workers were crowding natives out of jobs that were creating knowledge. We could expect positive effects to the extent that there are spillovers within innovation hubs that are not captured by individual level innovation. And what you're looking at the top is you can see I am interpreting it as a total derivative comprising all of those effects, and it is larger than the individual level effect, but not drastically larger.
Michael?
Yes, please.
One quick question here from David McKenzie. He's asking, Michael, how do you want us to think about inference here, or inference here, sorry. From a design-based perspective, we would want to cluster at the level of effective randomization. It doesn't seem like you would want to think that these CBSAs are all independent of one another. That is, what is it that led to the baseline differences in OPT STEM workers in the first place? Should we be clustering by industry structure perhaps, or using similar classifications as you did for low versus high patents?
Thank you. That's brilliant. I didn't mention, but I've just been clustering by CBSAs here, and I hadn't thought of that. And come to think of it, I believe that in the H-1B literature, there are at least variants in which other forms of clustering are explored. So David, thank you for coming, by the way, and that's a very good idea, and I just haven't thought about it enough. So I will. Another aspect of the plausibility here, I want to go back up to this plot. Just squinting at this, you can see that, well, if there is a treatment effect, it seems to be arising maybe 2 years after the shock already, which has struck some people who have seen this work as quite rapid. Isn't innovation a long-term process? Is it really the case that somebody showing up as a newly graduated OPT STEM worker is already causing innovation? First of all, I want to point out that 2 years after the shock could be 3 years after a person is working at a firm, in that what the 2008 reform did was take somebody who could have started there in 2007 and allow them to stay for almost 2 additional years after they began. So 2 years after treatment could be something like 3 years of work. I did show you examples of just anecdotes of high-skilled foreign STEM workers filing patents themselves 3 years after graduation, so it's not wildly implausible. But I really want to highlight the striking and just very creative and important work in that Bernstein et al. Paper that really worth a read if you haven't seen it. Again, they're doing this really brilliant and creative thing of linking Social Security data with data on patenting. The Social Security number data have the date of birth and the date of death if the person has died. And the Social Security number, actually the first 5 digits of the Social Security number that they have access to in this anonymized data contains information about the year in which the Social Security number was given, allowing them to identify immigrants, because it is typically immigrants who are given Social Security numbers much later than birth. And they can then ask the question, well, for those who died suddenly before age 60, and thus a really unexpected shock to a group of people who had innovated in the past, what happens to patenting by the people that they worked with in the past? And on the left here, you can see what happens to innovation by previous co-inventors after the death of a native, which is negative and modest, and what happens when after the death of an immigrant, which is really much larger and also immediate. And those are two very fascinating aspects. First of all, this doesn't suggest, and Bernstein et al. Don't interpret it in this way, that foreign inventors are somehow more capable in an absolute sense. It does suggest, and this is their interpretation, that they are often bringing to a team an important input that others and natives are not providing. So there's a complementarity of bringing different things, different approaches, different ideas to the table, not necessarily an absolute higher skill. But the reason I put these on the screen is just to show that this effect is instantaneous almost. In the very next year after the death of an immigrant inventor, the people around them are less inventive. And that's really, these are people who are passing away later in their careers. They're obviously not directly comparable to OPT workers just coming out of PhD programs or master's programs. But I do want to point out that some of these effects, we should not necessarily expect some of these effects to take a very long time to be realized. It's possible for some of these spillover effects, including substantial spillover effects, to be quite rapid.
Michael, so, just quick heads up, 4 minutes left, okay?
Thank you. The last thing I want to hit on is a major theme in the recent innovation literature has been this difference between patenting and innovation. Many patents are never cited. Many patents are never marketed. This is an actual real patent filed by my own grandfather in the 1960s. He was a plumber who invented a new kind of shower screen, which I still think is really cool, but he never did anything with it. So this is a patent that added zero value to the economy. Thank you, Grandpa. But so we really need to be concerned about whether patenting is measuring innovation in any sense. And a broad summary of the recent innovation literature has been that patents are certainly associated with value added, but that analysis that waits for the relevance or the usefulness or the economic value of patenting gets us closer to measuring the economic value of these things. Here in the first column, I've just got the same specification you've seen many times. If I weight by forward citations or forward citations just in the subsequent 5 years, the magnitude of that coefficient goes up. If I weight by the economic value of the patent as associated as measured by Kogan et al. In the QJE, where they link patent assignments at the firm level to CompuStat data on what happened to the market value of those firms when the patent occurred, to really more directly measure the economic value, the coefficient goes up substantially. When I weight by the backward citations to the scientific literature, estimated by Marx and Fuegi, also Bhavin Sampat does some work on this, we also see a higher coefficient. So these are, my interpretation of this table is that this is not just a bunch of useless paper that these OPT workers are causing, to the extent that this is a causal relationship, but in fact, they're doing exactly what one might expect them to be doing, which is, as science, technology, engineering, and mathematics workers, taking scientific knowledge and converting it into economically useful innovation. Bottom line, this evidence does not, to me, prove beyond doubt, but is consistent with OPT STEM workers at the margin of this large extension of the program, causing a substantial increase in real innovation and productivity in the economy, which is also consistent with the imminent termination of OPT in the United States, causing a substantial reduction to US innovation and even economic growth and productivity in the long run. So I really appreciate all of you being here, and all of the feedback so far, and I'd welcome even more right now. Thank you.
That's terrific, Michael. We are at the end of our time, but I just wanted to thank you for this terrific talk. And to everyone, the feedback link in the chat window went up. So if you have any feedback, just let us know. Also suggest some future speakers, and you can access the recording on the YouTube channel. There's a couple of more questions that I will just send to you, Michael,
Yes, please.
by email afterwards. But thanks so much for being here and giving this talk. Really fascinating.
And thanks to the questioners.
All the diagnostics in particular. Those were great, setting a model for future shift share papers. So thank you.
Thanks a million to all of you, and hope to see many of you soon.